Hello everyone and welcome to this electronical seminar on health and well-being by Invest Northern Ireland. My name is Lukas Westphal and my presentation today will present a couple of case studies on how novel approaches to increase the nutritional value of baked goods might be used and how these approaches might affect the final product quality. Before I get into this though, just very briefly about my background. I started my career in the food industry back in 2011 in a small to medium-sized artisanal bakery called Bäckerei Blümker in Germany. You can see the main production site here on the image on the screen. After completing a 3-year apprenticeship, I then moved on to do my undergraduates in Ökotrophologie, or also called Home Economics and Nutritional Sciences, at the University of Applied Sciences in Niederrhein-Mönchengladbach, which is also in Germany. After graduating from there, I moved on to the UK to conduct a master's in food science at the University of Reading. After graduating from Reading, I started my current role at Camden BRI as a senior bakery scientist. For those of you that are not familiar with Camden BRI, we are a membership-based food consultancy, the largest in the UK, with 2,500 member companies located in 80 different countries all over the world. Among our members are not only the top 10 UK retailers, but also the top 10 global manufacturers, and therefore we work with many of the world's biggest brands. One key element of our organization is research and innovation. All our members pay an annual membership fee, and a large proportion of this membership fee is used to fund what we call the member-funded research program. This research program is steered and voted on by all our members, and the topics of the research focus usually around the areas that you can see here on the screen. So the research projects we work on as part of this are usually related to quality and value, safety, nutrition, health, well-being, diet, but also other aspects like environmental sustainability, resilience and efficiency, or even skills and knowledge. Now, the project that I'm going to talk about first is part of our nutrition, health and well-being research program. The title of the project is Calorie Reduction and Fiber Enhancement. The project itself is steered by our nutrition and health member interest group. It's a 3-year research project, and we're currently almost coming towards the end of the 2nd year of the research. What we set out to achieve as part of this research project is, firstly, to help our members gain a better understanding of fibers, as well as their functions in different products. We set out to assess a broad array of available fibers. I'm sure you're aware the market of dietary fibers is very broad. There's a lot of different products available, and it can be very confusing to understand which product might be best suited to which application. Furthermore, we wanted to identify how dietary fibers might be used potentially to reduce calories in products, while at the same time maintain the product quality. However, we did not only want to gain a better understanding of commercially available fibers, but we also wanted to see and investigate how potential novel sources of dietary fiber might be utilized to improve the nutritional value of food products. Here on the screen, you can see a butternut squash, which is a vegetable that is commonly consumed in the UK and other parts of Europe. Usually, it is either consumed as a vegetable or very commonly also processed into soups. The first step that happens when butternut squash is processed industrially is that the outer layer is washed, followed by a removal of the outer layer. The skin is peeled off, or rather cut off by a knife. Usually these cut off pieces are not used for human consumption. The usual route would be that they're used either for animal feed or in a digester to produce electricity. So we wanted to investigate how perhaps we might be able to use these discarded pieces, this byproduct, to create a food ingredient that could be used in food products to increase the fiber content. And we've done this in a very simple manner by processing the outer skins that we received from a butternut squash processor, and we treated them with very simple processing steps, washing, drying and particle size reduction, and processed them into a dry ingredient that you can see here on the right at the right side of the screen. Here on the slide, you can see the composition of peels before drying. So first thing is important to note is that this is before drying. So you can see we have a relatively high moisture content, and therefore all other nutrients within these peels are not very concentrated in our material. However, already here in the wet peels, we have a fiber content of 3.4 grams, which of course has increased significantly after drying of the peels. We also tested different methods of drying to see what impact this might have on the peels and on the final product afterwards. So we tested a hot air drying technique versus a freeze dry technique. You can see the comparison of the two powder ingredients that we've created here on the screen. On the left, we have the hot air dried sample, which you can see has a bit more color, a bit more Maillard reaction, a bit more probably caramelization that had occurred during drying. While on the right side, we have a relatively pale powder that has been created from freeze drying. Both powders were dried to a similar moisture content of approximately 10%. After completing the development of our dry ingredient, we were on the lookout for a suitable food product application. And one product that seemed like a little bit like the obvious choice to us was a tortilla wrap. Reason for this is because if you go to the shops, what you can see there on the market is at the moment a very wide variety of colors and flavors. So it seems that this is something that's very well accepted among consumers currently in this product. So for example, you can see things like spinach wraps, you can see beetroot, for red colors, the green ones, the spinach, as I mentioned, but also spirulina powder, very commonly used. But even things like a pitch black tortilla is usually created using charcoal. You can find on the shelves that are very popular currently among consumers. So the next thing we did is that we used our created butternut squash skin powder in a tortilla. And you can see on the screen here the image at the bottom, which is our reformulated butternut squash skin tortilla. And I think it's very clear to see the very nice yellowish golden color that we've developed by utilizing our butternut squash powder in there. However, we did not only want to create new color, I think this was more the secondary result that we created. Mostly it really was about utilizing a byproduct, but also more importantly, increasing the nutritional content of our product. And if we take a look at this table here, we have the nutritional information per 100 gram from our control tortilla, and then from our redeveloped butternut squash tortilla, in which we use 20% butternut squash of our powder ingredient and replace 20% of the wheat flour with this. First thing that stands out here to me is very clearly the fiber content at the very bottom, which we've increased almost by 100% from 3.3 gram to 6.5 gram per 100 gram. You might also note that we've achieved a very, very slight calorie reduction from 295 kilocalories per 100 gram to 286 in our redeveloped product. However, you might also spot some downsides of this approach. For example, we've decreased the protein content from 8.2 gram to 7.6 gram, and at the same time, we've increased our sugars in our product quite significantly from 1.8 gram to 5.4 gram. Reason for this is that we've used our butternut squash peels as they were usually produced in industry, so in an industrial process as they are cut off. The thing that happens is that the butternut squash peels are cut off by a knife at the side. And of course, you can imagine this is not done very, very carefully, very accurately, very thin. No, but you also end up with a little bit or quite a significant amount of flesh attached to the peels. And of course, the peels are higher in carbohydrates, more starch, but also more sugars, which has led here to the increase in sugars. If we were to actually manually peel off the skins very, very carefully, very accurately, without getting too much flesh into our product, we would have very likely seen a higher increase in calories, but also nowhere near the significant increase in sugars that we have seen now. So our sugars would have probably stayed at a very similar level to what we had in our control formulation. The second case study that I'm going to talk to you about today is a research project funded by the BBSRC, which was mainly managed, organized and executed by King's College London. The project is about the bioaccessibility, but also the application of micromilled or micronized flour in bakery products. The team at King's College London have carried out a couple of studies which indicated that milling flour to a smaller particle size than usual might break down the outer layer, or certainly breaks down the outer layer, the aloyron layer of wheat flour to a smaller particle size, which might lead to a better bioaccessibility of minerals that are usually hidden in this indigestible outer layer of the wheat grain. So things like iron, for example, become better available to our body. Our input into this project was to investigate how does micromilling flour impact the quality of the final product. Before we look at the application in a bakery product, let's have a look at what micromilled actually means in terms of numbers. How much does a particle size of a micromilled flour change in comparison to a conventional milled flour? Here on the graph, we have a comparison of two samples. In red, we have a conventionally milled whole wheat flour, and then in blue here on the graph, we have the particle size distribution of a micromilled flour from the same grain, but treated differently with the added step of reducing the particle size further. On the y-axis here on this graph, you can see the density distribution, and then at the bottom, on the x-axis of this graph, we can see the particle size distribution per micrometer. The first thing that springs to mind when looking at this graph certainly is the very large peak that we can find here with our conventionally milled flour. So a lot of these particles are between 200 to around 900 microns is a very large area of our particles are within this size. Now looking at the blue lines here, the micromilled flour, we can see that this peak pretty much has disappeared and we have much more shift to a smaller particle size. With the majority of particles really range, well, we have the peak here in between 60 to around 90 to 100 microns. If we take a look at the X50, so the median particle size, which means that 50% of all particles within this flour lay under this value, we can see that the median particle size for our control flour was around 378 microns, while for our micromilled flour, this has now reduced significantly to 126 microns. Now, what impact does the smaller particle size have on the flour? Given that we've broken down a significant amount of the outer layer of the brown particles in our flour to smaller particles, they don't become as visible anymore in our flour. And we can see this here very well if we take a look at the color values of our flours in comparison. So here on this graph, you can see the L values of our flour color measurements. L value is a factor that L value is something that indicates the brightness of our sample. So for a sample that would be a clear, very bright white, we would have a value of 100, while a value of 0 would indicate a pitch black sample. And we can see here that our control flour had an L value of around 76, while for our micromilled sample, this has increased quite significantly to around 81 to almost 82, which indicates that the reduction of particle size led to an increased brightness of our flour. Now, I would say that this change in color, this increase in brightness of our micromilled flour does not only become apparent in the flour sample, but also very much in the finished product. So here on the screen, you can see two samples that we've created in our test bakery. One of them has been made with 100% whole wheat, while the other one has been made with 50% whole wheat and 50% of a strong white bread flour. However, you can still see quite a significant change, a significant difference between the two samples in terms of their color, in terms of the brightness. So the one on the left is a sample made with 100% wholemeal flour, but at the same time does appear still brighter than the sample on the right, which only contains 50% wholemeal flour, but milled to a larger particle size. However, there are not only advantages of using a micromilled flour. Flour is a smaller particle size. Here on the screen, we can see the specific volume of bread samples that we made as part of this project. On the left-hand scale here, you have the specific volume, the y-axis specific volume in milliliters per gram. And then at the bottom, you can see the different samples that we've created, which is samples using wholemeal flour ranging from 25 to 100%, as well as a comparison always between wholemeal milled conventionally and then wholemeal milled to a smaller particle size micromilled. The first trend that I would say is obvious here from the graph, a very general trend, which is not surprising, is that using a higher amount of whole wheat flour generally has led in our experiments with breads to a smaller volume of the product. So using more wholemeal flour has led to a smaller volume of our product. So we've created smaller breads, which is really what we've expected to see. We have a lot more bran particles in our product. Consequently, there are more bran particles that are able to interrupt our gluten network, which of course impact on the gas retention capabilities of the dough, leading therefore to a smaller volume of the product. However, there's a second trend here in the graph that's not as obvious. However, if we always compare the two samples that contain an equal amount of wholemeal flour, it becomes obvious that, for example, the two first here, 25% wholemeal flour conventionally milled versus 25% wholemeal flour micromilled, that the micromilled sample always is a little bit lower. We can see this here for 25%, a little bit smaller volume than the conventionally milled one, same trend here for 50%, and even for 75% and 100%, always a little bit smaller volume than the conventionally milled sample. Reason for this simply is that by decreasing the particle size, what happens is that these bran particles that don't really contribute to the structure, don't really contribute to the stability of our dough network, they start to interrupt the gluten network. And you can imagine the more of these little particles we have with our network, so if we reduce the particle size, the total number of bran particles will increase within our dough matrix, leading to multiple more physical interruptions within the gluten network, and therefore weakening the structure much more significantly than larger bran particles would. So this brings me to the end of my presentation. Thank you all very much for listening. If you would like to find out more about Camden BRI or any of the projects that I've presented today, please don't hesitate to get in touch. My contact details are here on the screen, and I look forward to hearing from you. Thank you all.